Okay, sir. If you actually, I worked with Professor Dubey, Balram Dubey ji.
Okay, from BITS Pilani.
No, I did my PhD from Tezpur University when he was here.
Tezpur.
He initially joined Tezpur. That time, sir. That was around 96, 97, I think.
Okay. Yeah. So that is Central University, I think now.
Yeah. It is a Central University.
So shall my show my slide, or is it?
You can just check it, sir. Share your screen.
Can you see?
Yeah, it is visible, sir. You can enlarge it. You can go to slide mode, I think. It is fine, sir. Just try and change the slide, sir. Let us see. Sometime. It is changing, yes. No problem. So, shall we start, sir? Okay. Dear participants, good morning, all of you. And I have the privilege to introduce Professor O.P. Mishra, a distinguished researcher and academician. So, Professor Mishra is the head of School of Mathematics and Allied Sciences, Jiwaji University, Gwalior. He did his PhD from IIT Kanpur. His areas of research include mathematical modeling in ecotoxicology, mathematical modeling in population and community ecology, mathematical modeling of infectious and communicable diseases. He visited International Center for Theoretical Physics, Trieste, Italy twice, College of Natural Sciences, University of California, Berkeley, USA, and Rajamangala University of Technology, Thaniaburi, Thailand. He received Boy Scouts Fellowship of DST, New Delhi. He has published 93 research papers in reputed journals of reputed publishers like Elsevier, Springer, and World Scientific. He guided 15 PhD research scholars, 37 MPhil have been awarded under his supervision. He is the Dean of Science Faculty and Executive Council member of Jiwaji University. He has published 2 books, and he is a member of editorial board of American Journal of Computational and Applied Mathematics, executive member of Indian Society for Mathematical Modeling and Computer Simulation, vice president of Mathematical Society, Banaras Hindu University, Varanasi. He has completed 4 research projects and has delivered 21 invited lectures in various universities across the globe. With these words, I welcome Professor Mishra and thank him for sparing his time for all of us. I hope all the participants will be benefited by his experience and his lecture. So, sir, welcome, and you can start your lecture. The floor is yours.
Okay, thank you, Dr. Jamal Hussain, for your kind words and introducing me to the audience. Good morning to all the participants. I am audible to you, Hussein, Dr. Hussein. Am I audible, Dr. Hussein?
Yes, sir. Yes, sir. Yeah, very
Okay.
much audible. Yes.
So actually, I have chosen the topic related to the mathematical modeling in population ecology, because most of the speakers I have seen that they are speaking on infectious diseases and communicable diseases. Although it's one of my area, and I have recently published papers on COVID and malaria dengue in 21. So, but I thought it would be something different to talk about the population ecology, how we go about the modeling and looking at the effect of toxicant when the predators are going under harvesting. So this basically this has been also a published article in International Journal of Applied and Computational Mathematics of Springer in 2017. So the title of my today's talk is Modeling the Effect of Toxicant on a 3-species food chain system with predator harvesting. So we know that due to the anthropogenic activities, a huge quantity of pollutants toxicant enter into aquatic and terrestrial environment, causing deleterious effect on living beings and their resources. In a food chain system, it is noted that there is an indirect negative effect on predators if their prey populations are exposed to toxicant. Mathematical studies related to the effect of harvesting on the dynamics of prey predator populations have been carried out by several researchers. It is being widely studied, prey predator dynamics under harvesting, and some few authors have also studied the prey predator system with predator harvesting only. The presence of toxicant decrease the growth and productivity of the affected species as well as the carrying capacity of their environment. In recent years, however, several investigators have studied the effects of toxicant on biological species in polluted environment by using mathematical models. Some research work have been also carried out on the survival or extinction of species in 3-species food chain systems under the effects of toxicants using mathematical models. So basically, the food chain model has been also studied using mathematical model, and their stability analysis and bifurcation analysis has been carried out. Basically, in food chain model, we have one prey and then one intermediate predator who is depending upon the prey. Then there is a top predator who is that top predator depends upon the intermediate predator. So there is a chain type of system in this. So in literature, we generally mostly find the studies on the prey predator system, considering different types of basically functional responses. But I have taken so there are few food chain models in which either the effects of toxicant has been considered. There are few of mine also which has been published, and or they have considered the role of harvesting in predator population. So I thought, what could be the effect of both the toxicant and the harvesting on the predator population? So keeping this problem in view, I studied this paper and made mathematical model for the food chain to study the dynamics of food chain population, food chain system under the effect of toxicant and harvesting. So basically, in this talk, two nonlinear mathematical models are discussed to observe the effect of toxicant on a 3-species food chain system with Leslie Gore model undergoing harvesting of intermediate and top predators. The model is analyzed qualitatively and the results are supported by numerical simulation. So the numerical simulation has been carried out, I should first tell you, not on actual data, but on hypothetical data, just to support the analytical results. So in this mathematical model, we have considered a 3-species food chain system and studied the effect of toxicant with predator harvesting to visualize the dynamical behavior of prey and predator populations. The effect of constant yield harvesting is considered in the predator population of model 1, and the effect of constant effort harvesting is considered in the predator population of model 2. So basically, in this lecture, I am going to deal with two models, one with constant harvesting yield and other with constant effort harvesting. So this is the first model, which I call it model A, considering the effect of toxicant and constant yield harvesting. So first I should say what is constant yield harvesting term. This H1 and S2. H1 and S2 are the constant yield harvesting terms. So because we are harvesting the intermediate predator and top predator, that is X star is the density of the intermediate predator population, and Y star is the density of the top predator population. So since we are undergoing harvesting, that means we are killing this predator population. So we have a negative effect on their growth rate. So we have taken a minus sign in both the terms. Now I start with the first equation. The first equation is for the prey population. So N star denotes the density of the prey population depending upon the time. And their growth is being considered to be a logistic growth. Those who have studied mathematical biology or biomathematics, they must be knowing about the logistic growth. But I should tell you about this, that Rn is the growth rate, and R is the intrinsic growth rate or specific growth rate, R. K is the carrying capacity of the population. So basically, this is resource dependent growth term. So we have assumed that the prey population is growing logistically by considering the term Rn star 1 minus n star by k. Then due to the predator, that is X star, intermediate predator, their growth rate decreases. So here this A1 n star upon B1 n star, this is basically the intake rate of the predator population, which is depending on the density of the prey population. And this type of this was considered as a functional response and was named as Hawling type 2 functional response, A1 n star upon B1 plus n star. So this term is your Hawling type 2 functional response, and X star is the predator population, intermediate predator population depending upon the prey n star. A1 is the basically the maximum growth rate or maximum intake rate, and B1 is called as the half saturation constant. B1 is called the half saturation constant, means when you take B1 equal to n stars, so your maximum intake rate becomes A1 by 2. So this is what we call it, the half constant, half saturation constant as B1. And basically this is also a monode type of equation, A1 n star upon B1 plus n star. So since the predators are killing the prey for their survival, so we have a negative term here. Then Q, we come to the intermediate predator population, that is X star denotes your density of the intermediate predator population. So here Q, this term is multiplied by the Q, because Q is called the conversion coefficient or conversion rate. So whatever is food the predator takes in from this predation rate, so that is converted into their population, and that is called the Q. Q is your conversion coefficient, and it lies between 0 and 1, because all the food is not used in growth of the population of the predator. So therefore Q is always between 0 and 1. Then we have another top predator Y star, which is depending upon the intermediate predator X star. So here we have considered Lotka-Volterra type of interaction here, and so minus A2 X star Y star, A2 is the predation rate, and since due to their interaction between the top predator and intermediate predator, top predator is killing the intermediate predator, so their population will decrease. So we have a negative sign. So this term is your predation by the top predator, and then we have considered the role of toxicant in the intermediate predator only, not in prey or top predator. We have just considered the role of or effect of toxicant in the intermediate predator. So this term is your the effect of toxicants. So effect of due to the toxicant, C0 is the organismal toxicant. So let me tell what is C0 actually. So first we have to come to this equation. C is dC star by dt. So C star is the concentration of toxicant in the environment. C star is the concentration of toxicant in the environment, and which is Q0 is the input rate of the toxicant in the environment. Q0 with the constant input rate. We have taken Q0 to be constant input rate of the toxicant in the environment. That is being depleted. Natural depletion is there. So natural depletion. So we have minus sign, and S3 is the natural depletion rate of the environmental toxicant. Then due to the interaction, your intermediate population is interacting with the environmental toxicant. So this term is the interaction. So because the they are taking the toxicants is going inside the predator population, so the density of the environmental toxicant is decreasing, and also due to that this C star. So this is the depletion of the environment toxicant due to the consumption by the predator, intermediate predator population. C1 is the consumption rate. So now this is, since this has gone inside the population, so that's why we call it, this goes to the C0 star equation, which is your C0 is called the organismal toxicant concentration, which is inside the population of the top intermediate predator. So this goes to this. So this is the increase in the organism concentration of the toxicant. Then there is a natural washout from the body. So this is your minus S1 C0 is a natural washout from the body. So we have a decrease minus sign over here. So decreasing organism concentration are decreasing with this rate S1. Then because of this minus, so this interaction, so C is interacting, X star is interacting with the C, so their growth rate will decrease on account of the concentration. So C0 is basically actually when we do not take CE here, because the predator has consumed the toxicant from the environment, and then it has gone to the body, and then it starts affecting the predator. So actually the C0 organism concentration of the toxicant is affecting the predator population, intermediate predator population. So we have a C0 over here. Now this D0 X star, D0 is the natural death rate of the intermediate population, and as I told, this X1 is the constant yield harvesting. Now we come to the top predator equation Y star. Y star is the density of the top predator population. So here the R2 is the growth rate or natural growth rate of the top predator, and so this BX star, this basically when if we write if this is going logistically, basically this top predator is going logistically, as you see here. So here K is being considered, that is the carrying capacity of the top predator is considered to be proportional to density of the intermediate predator population, on which Y star is depending. So BX star is basically the intermediate predator population dependent carrying capacity. And this is so here it was here we have taken to be a Holding type interaction with functional response between N star and X star, but between X star and Y star, this is basically was given by the Leslie-Gower. So here we have taken the Leslie-Gower type of interaction between X star and Y star. S2 is your constant yield harvesting. Now the X star will die out, and due to their death, their organism concentration will decrease. And since it is a non-degradable toxicant, it will again will come into the environment. So the concentration of the environmental toxicant will increase because it again comes to the environment because it is a non-degradable toxicant. So this is how the whole model goes on. Now we have considered in initial conditions. So all the initial conditions of the variables n star, x star, y star, c, and c star are considered to be greater than 0. But since when we are going to study initially the dynamics or of the food chain model under the toxicant and harvesting effects, and we consider that the organism concentration is 0 initially. Like when we talk about the SIR model, you consider R initially R to be equal to 0. That is remote population or recovered population. So I will again quickly tell you the parameters which I have already explained in the model A. So R and K describe the intrinsic growth rate and carrying capacity of prey in the absence of predators. A1 and B1 are maximal predation rate and half saturation constants for intermediate predator. Q is conversion factor. A2 is the loss of intermediate predator due to the top predator. B2 is the death rate of intermediate predator due to organism concentration. D0 is the natural death rate of intermediate predator. R2 is the intrinsic growth rate of top predator. Bx is the role of intermediate predator dependent carrying capacity for top predator. B is a measure of the quality of the food for top predator. H1 and H2 are the constant yield harvesting on the predator population. Q0 is the external input of toxicant into the environment. The toxicant are assumed to wash out from the environment as well as from the organisms at rate S1 and S3 respectively. C1 is the removal rate of toxicant from environment due to uptake by the intermediate predator species. S2 is the removal rate of toxicant from the intermediate predator species due to its death. It is assumed that the growth rate of uptake concentration of organism C0 star increases by the same amount as the depletion rate of toxicant concentration CET in the environment and is assumed to be proportional to the intermediate predator population as well as the environmental concentration of the toxicant, that is C1 X star CE. Also, it is assumed that the uptake concentration of organism may decrease with rate coefficient S2 greater than 0 due to decaying of intermediate predator population and which may re-enter into the environment, that is at the rate S2 X star C0 star. So the references are already mentioned in this, from where we have considered these terms. Now there are number of parameters in the model A, so we will try to reduce the number of parameters by considering these scaling factors: n equal to n star by k, k equal to a1 x star by k, y equal to a1 y star by r, c0 equal to r c0 star by s2, c equal to r c star by c1, and t equal to r t star. So with this scaling, we get this model 1, which is the some people call it non-dimensionalized model also. So this is the non-dimensionalized model. So we will, for the qualitative analysis, we will study this model 1. But for numerical simulation, we will study we will do the numerical simulation using the original model without scaling. So these are the parameters of the model 1 after scaling. All these parameters are of course assumed to be only positive values. Then in the second model, everything is the same as model A. In the model B, everything is same as the model A, but only we have considered here this term. Instead of the constant yield harvesting, we have considered it to be constant effort harvesting. E1 is the rate of effort, and which is E1 is the rate of effort of harvesting, which is considered to be constant. And since here it is the harvesting is done at the rate E1, and here we have multiplied it with the population X star, because the harvesting effort is applied on the population existing. So minus E1x, because of the harvesting we have minus here, So this is a very minus U1x star is an harvesting. The total is called the harvesting yield. Like H1 equal to H1 was considered to be constant harvesting yield. Now here this harvesting yield is now density dependent, and E1 is the constant effort for harvesting. Similarly here minus E2 by star. So instead of the constant yield, we have considered to be density dependent y star, and E2 is the constant effort harvesting rate. Rest the equations for the food chain model is same. The state variables and parameters of the model B are the same as defined in the model A, except E1 and E2, which define the constant effort harvesting for X and Y respectively. Similarly, in model B, we can reduce the number of parameters by the model A scaling transformations, even if for our numerical test, we will continue to use the original system. As I said, for numerical simulation, we will use the original system, but for qualitative analysis, we are going to use the model 1 and model 2, which are the scale models. This is model 2, which is a scale model of original model B. Here E1 0 equal to E1 upon R and E2 0 equal to E2 by R. And rest I have already defined the terms, parameters and constants. Now we have a set of system of nonlinear differential equation, as you have seen. Now, if the first thing what we do in the analysis of these type of mathematical models in ecology, we have to see that whether our these variables n, x, y, c, c, they lie in some bounded region or not. That bounded region means if the region in which the solution will start and will remain that region only for in the future time also. So boundedness is very necessary. Otherwise, for an unbounded solution, we will come to no conclusion. So first we do the boundedness, and omega 1 is the bounded set. So omega 1 is a region of attraction for all solution initiating in the interior of the positive region, and where all these are given. And the proof is by using a comparison theorem, which is this. So using a comparison theorem, we can do this, find out the regions, bounded regions, like M1. So W2 equal to U2 C0. So this is very routine things the people in ecology modeling are doing. So after boundedness, the other thing is that we generally find out the equilibrium of the model. That is the equilibrium point of the model, or steady state, or fixed point, or critical point, whatever you call. The model 1 has the following 4 non-negative equilibria in N, X, Y, C0, and C space, namely. E1 0 is basically a non-harvesting equilibria, so we are not interested in that. E1 1, E1 2, E1 2 tilde, E1 1 double dot, E1 3 bar. So these are the 3 equilibrium points in which we are interested, and then we have to find out the values of these equilibrium points. So sometimes we are not able to find the explicit values of the equilibrium points, so we go for the isocline analysis, or some other technique like making it to be a polynomial and then finding out the positive root using Descartes' rule of sign. So, but here when we talk about the E11 equilibrium point, E11 double dot equilibrium point, so we see that N double dot 00 C0 double dot C. Here we have got the values. N double dot equal to 1, C0 double dot equal to 0, and C double dot equal to U0 upon E5 respectively. So here we see that the prey population is there, but intermediate population and top intermediate predator population and top predator population are absent in this. And this is a boundary equilibrium point. E11 double dot is a boundary equilibrium point. The next equilibrium point is E1 to tilde, N tilde, X tilde, 0, C0 tilde, C tilde. So far here we are not able to find out the explicit value of these equilibrium points. So here we do the isocline analysis. What we do, we write from the equations from the isoclines. Isoclines we get by putting all the derivative to be equal to 0. So from there we get the isocline by putting all the like here, when dn by dt equal to 0, dx by dt equal to 0, dy dt equal to 0, dc 0 by dt equal to 0, dc e dt equal to 0. So when we put all this to be equal to 0, so we get the isoclines. So in this case we are getting 5 isoclines. Yeah. So when we take derivative to be equal to 0 for the n, x, y, c0, c, that means we are talking about the steady state solution, which we call it also an equilibrium point or equilibria. So we get from equation 2 x equal to as a function of f1n. From equation 3 we get c0 equal to f2n, and from 5 and 6 we get c equal to f3n. So we see that if we find out the value of n, then we can find out the value of x, c0 and c. So for finding out the value of n, we take away isocline number 4 equal for the equation number 4, and then we get f of n equal to e1 f1 n f3n minus f2n e4 plus e1 f1n. Basically there is some mistake. This is u3 f1n, and then what we do, we see that when f0 we put n equal to 0, f0 equal to this expression which is greater than 0. Then we take when f equal to k0. So when f equal to k0, we get e1 f1 k0 this, and this is f of k0 is less than 0. So there are two values. We have f0 is positive and fk0 is negative. That means our root of this equation number 16, will lie between 0 and k0. So this guarantees the existence of a root of fn equal to 0 for 0 less than n less than k0, say n tilde. So this is a very simple result. We all know that for any polynomial, if you have at one point it is positive, other point is negative, then the root of that polynomial will lie between those two values. We use it in bisection method also when we do the numerical analysis. So now we come further. This root will be unique provided the derivative of f will be negative. So we found out the derivative of f, and where f1 dash n, f2 dash n, f3 dash n are given this. So you can see that finding out the studying the existence of the roots, existence of the equilibrium point, it's not that simple. So because it is a non-linear mathematical model, so most of the time we have to go for the existence of the equilibrium point. Otherwise, if we don't find out the equilibrium point, then we cannot get the existence of the equilibrium point, then we cannot go for their stability analysis. So there is the mathematical complications are there when we talk about the existence of the equilibrium points, and when we have a more number of equations. So generally the people study only prey predator or two equations they take, not food chain. So food chain is not very widely studied. So knowing the value of n tilde, the values of x, c0 and c can be computed from equation 13 to 15 respectively, as I said. So now existence of this interior equilibrium point E1 3 bar tilde. Here all the variables, n, that is prey, intermediate predator, top predator, organismal concentration, and your environmental concentration of toxicant, they are considered to be positive. So this is called the interior equilibrium point. Here also, to find the existence of the E1 3 bar, we do the isocline, use the isocline method. So from 2 as before, we get x equal to g1n. From 3, we get c0 equal to g2n of y. From 4, we get x equal to g3y. From 5 and 6, we get this expression g4ny. Now considering two functions from 2 and 6, g1ny equal to 1 minus n, 1 plus e1n minus a1 g3y, and g1 2ny equal to u0 minus g4ny e5 plus u2 g1n plus u2 g1n g2n comma y. These are all expressions we get from the isoclines. For existence of n bar and y bar, the two isoclines g11ny and g12ny equal to 0 must intersect. We note that g11 0 equal to 1 and g12 0 equal to this expression, which is positive greater than 0. Now g12 0 0 is greater than 0 if 1 is greater than u1. This is the condition for this to be positive, and this also. So there are two conditions: 1 greater than u1 and u0 alpha 1 e3 1 minus u1 greater than d1 plus alpha 1 h1 alpha 1 u2 u4 plus e3 e4. So under this condition, this g1 to 0 is greater than 0. Now g11 n and 0 is 0, then n will have one positive root, say psi 1, from the following quadratic equation of n. So when we put g1 n 0 equal to 0, we get this quadratic equation, and it will have a one positive root, say psi 1, when 1 is greater than e1. So here we are using the Descartes rule of sign to show that there is one positive root. Now g1 0 y 0, then y will have one positive root, say y psi 2, from the following quadratic equation, which implies y. So we have solved here the quadratic equation and got the value of y, which is supposed to be greater than 0 if delta square is greater than 4 alpha and beta s2. So a lot of mathematical calculation is being used here to do the existence of the equilibrium point. So g12 n 0 is 0, then n will have one positive root, say psi 3, from the following 4-degree equation of n. So here also you see that this is a 4-degree equation and there is only one change of sign. So we will have one positive root, psi 3, where the value of b11 and these are all given. Then g1 to 0 y equal to 0, then y is this much equal to psi 4 if u0 alpha 1 e3 plus d1 alpha 3 plus alpha 1 square h1 t3 is greater than d1 u2 plus alpha 1 h1 u2 and u2 e3 is greater than alpha 1 e2 e3, where t3 equal to e5 plus u2 by alpha 1. A lot of mathematical calculations are there here. Just I wanted to tell that the existence of showing the existence of equilibrium point is not that simple. So existence of interior equilibrium point E13 of the model. So you can see from figure 1 that when there is an interaction of the two isoclines G11 this one, as I said, G11 ny equal to 0 and G12 ny equal to 0, they will intersect. In two cases, when psi 3 is greater than psi 1 and psi 2 is greater than psi 1, you can see here. So psi 1, psi 3, psi 4, psi 2, psi 4, they are all the values which have been found earlier. And under this condition also, under this case also, they will have value. So you see that the two isoclines G11 and G12 intersect, and we get the value of x bar and y bar, x bar and y bar here. So thus both the isoclines intersect each other in the region G13 and y 0 less than y3 and y less than this. In the following two cases, which has been shown in figure 1, the point of intersection will give n bar y bar. For uniqueness of n bar y bar, we must have dy dn less than 0 for both the curves in the region G13. For curve 23, this curve G11 ny, dy dn is less than 0, and for curve 24, that is g1 to ny, dy by dn is less than 0. So we have seen that dy by dn is 0 for both g11 and g12. So there is a uniqueness of n bar and y bar. So once we have found out the n bar and y bar, then other equilibrium points can also be found out. In case 1, the absolute value of dy and dn given by 27 is less than the absolute value of dy by dn given by 28. For the case 2, just the opposite is the condition. Knowing the value of n bar and y bar, x bar, 0 bar, and c bar can be computed from the equation 17 to 20, which we have shown earlier, 17, 20, x. And c. So all depending upon n and y, x bar, c0, and c, they are all depending on n and y, and we have found the existence that the equilibrium point, the value of n and y bar, they are given in the positive phase plane. Actually, this is phase plane. Figure 1 gives the phase plane of n and y. Now we come to the dynamical behavior of the model 1. That means we are going to do the local stability of the model 1. The trivial equilibrium point, that is equilibrium point without harvesting, is shown to be unstable. And because there is one root which is positive, there are two roots which are positive, so this is unstable. The equilibrium point E11 as the eigenvalues of the characteristic equation are this, and we show that E11 double dot is unstable. The equilibrium point E12 tilde, one eigenvalue of the characteristic equation delta, and another 4 eigenvalues are given by the roots of the following equation. Where this, if the root Hurwitz criteria is satisfied, then all the roots of 29 will be negative. The root Hurwitz criteria mentioned above satisfied if E5 by E1 minus E2 greater than X bar. So there is a root Hurwitz criteria for a polynomial which says that which has conditions. So under that condition, the roots of that polynomial will be negative if real, or they will have a negative real part if complex. So using the root Hurwitz criteria, we study the stability analysis, or we do the stability analysis. And we know that for stability, all the characteristic roots or eigenvalues should be negative. And if one eigenvalue is positive, it will be unstable. So these are the basic concepts in stability theory, for the linear stability theory. Now this is the interior equilibrium point. The characteristic equation of the equilibrium point E13 is written as this. So you get by your making these equations, you get by characteristic equation, you get by finding out the community matrix or Jacobian, and then evaluating that community matrix at the equilibrium points, you get the characteristic equation, and from that characteristic equation you find out whether the roots are negative or not, and then you do the you find out the conclusion for the, or do the stability analysis of the equilibrium, particular equilibrium point. So this is the basic concept of linear stability. So according to the root Hurwitz criteria, E13 bar is locally asymptotically stable provided these conditions are satisfied. Now we have also shown that the equilibrium point, the positive equilibrium point or the interior equilibrium point E13 bar is non-linearly stable in the region omega 1. So for that we have used the Lyapunov function, and you know that the when you find out the Lyapunov function and when you find out the solution, when you calculate the derivative of the Lyapunov function, Lyapunov function means it should be a positive definite function. Lyapunov function you take, it should be a positive definite function. That is, it should be positive definite function means the function is positive for all non-negative values. Sorry, for all positive values, and it will be 0 for 0. So that is the Lyapunov function. So there is no actually particular method for finding out the Lyapunov function of any nonlinear system, but generally some square energy term, that is square term or logarithmic terms, are taken for the Lyapunov function. And when we find out the derivative of the Lyapunov function along the solutions of the system, And if it turns out to be negative, then we say it is asymptotically stable. And if it is positive, we say that the system or the equilibrium points are unstable. And non-linear stability means we are not ignoring any non-linear terms in the equation. As in the linear stability, we take only the linear terms. So, so if the following inequalities hold in the region 1, these are the inequalities. Then the positive equilibrium point E13 is non-linearly stable with respect to all solutions initiating in the interior positive region omega 1. So method, the stability by Lyapunov method is basically a sufficient, not a necessary. So just I will tell what type of Lyapunov function we have considered here in this stability. So we consider the following positive definite function about E13 bar, that is B1 n minus n bar log n by n bar. For x we have considered to be x minus x bar whole square. For y also we have considered square term, and for C0 also square, and for C square. So this choosing Lyapunov function or making Lyapunov is just it's an art. There is not such any fixed criteria for making this. So now differentiating V11 with respect to time t, we get this. Using system equation 2 to 6, we get after some algebraic manipulations, dv1 dt equal to this. Now dv11 dt can further be written as sum of the quadratic forms as this, where these are this. Now by using Sylvester criteria and by choosing m2 equal to m3, m4 equal to 1, these all m2, m3, m4, they are all arbitrary constants, so we can choose accordingly. dv11 dt is negative definite under the following condition. We note that the inequalities 31 implies this. So all the inequalities which I have mentioned in the lemma for proving the non-stability analysis comes from 58 to 64. So hence B11 is a Lyapunov function with respect to E13 bar, whose domain contains the region of attraction omega 1, proving the theorem. Now, similarly, we do the boundedness of the model 2. And here we observe that model 1, model 2 have the same boundedness criteria. So the same reason we have the same reason of attraction is being considered for the model 2 also. Equilibrium of the model E20 is the trivial equilibrium point, that is non-harvesting equilibrium point. E21 double 4 dots, E21 double tilde, E23 double bar. So these are the notation for the equilibrium point of the model 2. The existence of E20 is obvious. We prove the existence of E214 double dot, E22 double tilde, E23 as follows. So here, in the case of the equilibrium point E214 dots, we get the explicit values for n, C0 and C respectively, and x and y are 0. Existence of this, again we do the same isocline analysis as we have done in the case of existence of equilibrium point of model 1. Cx equal to h1n, C0 equal to s2n, C equal to s3n, and we have taken hn equal to this. Hn we get from the equation number 4, this one. Here also it should be u3. Instead of u1, it is u3. Then we know that similarly as we do, 0 equal to at 0h, at 0 is positive, and at k0 it is negative. So in this case also the roots will lie between 0 and k0, say n bar, n double tilde. This guarantees the existence of the root of hn equal to 0 for 0 less than n less than k0, say n bar tilde. Further, this root will be unique provided s dash n is less than 0. which we have shown. Knowing the values of n or tilde the values of x, c0 and c can be computed from the equation 38 to 40 respectively. You can see here from 38, 39 and 40 you can find out the value of c, c0 and x. So this is the existence of E22 double tilde. Now existence of the equilibrium point E2 3 double bar. Here also we have taken x equal to as J1n from equation 8, from 10 y equal to J2n, from 9 C0 equal to J3n, and from 11 and 12 C equal to this J4n. Let Jn equal to U1 J1n, J4n minus J3n, E4 plus E1 Jn. So here this is also E1, instead of E1 it is U3. Then we note that J0 is positive and JK0 is less than 0. This guarantees the existence of the root of Jn equal to 0 for 0 less than n less than K0, say n bar, n double bar. Further, this root will be unique provided J dash n is less than 0. Knowing the value of n double bar, the values of x, y, c0 and c can be computed from the equation 42, 45 respectively. So this was the existence of the equilibrium points of the model 2. Then similarly we do the local stability analysis for all the equilibrium points, and we find that the trivial equilibrium point E20 is unstable. Equilibrium point E214 dot is locally asymptotically stable under the condition 47 and 48. They are all parameter dependent condition. Then equilibrium point E22, one eigenvalue of the characteristic equation is delta less than E20, and the other 4 eigenvalues are given by the roots of the following equation. So here we use the root in 49 we use the Routh-Hurwitz criteria for finding out the nature of the roots of the polynomial 4-degree polynomial 49. So according to the Routh-Hurwitz criterion, E2 is locally asymptotically stable provided that E5 by E1 minus E2 is greater than x double tilde is negative. If V1, V1, V2, V3 greater than V3 square plus V1 square V4 is satisfied. The characteristic equation of the equilibrium point E23 double bar is written as this. This is the interior equilibrium point. That is, we also call it an coexistence equilibrium point. Coexistence, all the species are surviving. The E23 double bar is stable, then we can say it is a coexistence equilibrium point because all the one prey and two predators are all surviving. So that's why interior equilibrium point is also called the coexistence equilibrium point, provided it is stable. So we get the characteristic equation as 50. It's a 5-degree polynomial. Again, we use the Routh-Hurwitz criteria to find the nature of the roots, and if the conditions of the Routh-Hurwitz criteria are satisfied, then we say that the interior equilibrium point is locally asymptotically stable. From these complicated expressions, it is however difficult to interpret the results in ecological terms. Therefore, they are verified numerically. Numerical examples are taken and graphs are plotted to illustrate the dynamical behavior of the system about equilibrium point E23 double bar. So generally, we have carried out the numerical simulation for interior equilibrium points for of model A and model B. Now the equilibrium point, interior equilibrium point of the model 2, that is E23 double bar, is also non-linearly stable in the region omega 1. And for this, we have a theorem. The following inequalities hold in the region omega 1. Then the positive equilibrium point E23 bar is globally asymptotically stable with respect to all solution initiating in the interior of positive region omega 1. So for this also we have considered same type of Lyapunov function. You can see over here B21 positive definite function. So for n0 x bar 0, so for n equal to n bar, x equal to x double bar, y equal to y double bar, c0 equal to c double bar, c equal to c double bar, the V21 is 0. And for all other n not equal to n double bar, x not equal to x double bar, y not equal to y double bar, C0 not equal to C0 double bar and CE not equal to C double bar, it is a positive definite function. It is positive always. So again, differentiating V21 with respect to time, we get D2V21. So we are respecting this with respect to time, we get this. Then putting the values of dn by dt, dx by dt, dy by dt, dc0 by dt from the equation of the model 2, we get after some algebraic manipulations, dv21 dt equal to this. So this is a long expression, and we find out after a simple calculation that dv21 dt is less than a quantity given on the right hand side of the equation, where all the b1 and they are mentioned in this. Now by using Sylvester's criteria and by choosing n2 n4 equal to 1, n2 n4 are arbitrary constants, so we can choose it. dv21 dt is negative definite under the following conditions, and these conditions from 67 to 71 gives you these conditions of the theorem. So, this theorem. Now we come to the numerical simulations. So as I said that the numerical simulation, the values of the parameters will be taken hypothetically, and numerical simulation we will use the actual model A and model B, not the scaled model. So in this section we demonstrate the dynamical behavior of a 3-species food chain system with predator harvesting in the presence of toxicant with the help of numerical simulations to facilitate the interpretation of our mathematical models. The figures 2 to 20 illustrate the stability behavior of all the equilibrium points of the models for the given sets of parameters, and the graphs have been plotted with the help of MATLAB. Numerical simulation for model 1. So we choose the following values of parameters for E13 bar. So these are the values we have taken. It is found that under the above set of parameters, the equilibrium point E13 bar is locally asymptotically stable. So E13 bar is your interior equilibrium point of the model 1. So in this we have found with these parametric values we find out we have shown that E13 bar is non-linearly stable in region omega 1, and also it is locally stable or linearly stable. So we got n double dot equal to this value, x double dot equal to this y. So we see that all the values are positive, and it is a locally asymptotically stable, seen in the figure 2. So when we choose this parameter of the parameters of the model, that is constants which we use in the model, so it should we should choose in such a way that it should satisfy all the conditions related to existence of equilibrium point and also conditions related to stability. So then only we can take these parameters. If they do not satisfy the conditions of the stability or existence of the equilibrium point, even the boundedness condition, then we will not consider this parameter. So we have to choose another parameter. So choosing this parameter is also very tedious job, or it's very difficult. So now because generally for such type of complicated models, we don't have any do not get the real data, real world problems. So this equilibrium point, the positive equilibrium point or interior equilibrium point of the model 1 or A E13 bar is locally stable, and this is given in the numerical values are given here. You can see here n double bar, this x dot, double dot, n double dot, y double dot, c0 double dot, c double dot. So this is the figure 2, and you can see that figure from 2 that all the equilibrium points are stable here. Time series graph for the model 1 around the equilibrium point showing the stability behavior. See, all are approaching the equilibrium values. All are these trajectories for n, x, y, c0, c are approaching their equilibrium values. Now numerical simulation for model 2. We choose the following values of parameter for E2 to double tilde. With the above values of parameters and taking the remaining parameters to be same as considered for E21 4 dot, it is found that under the above set of parameters, the equilibrium point E22 double tilde. So we find out the with these parameters, we find the value of n double tilde to be 8.3943 x double dot, this y double dot, it is 0, c0 dot, this 0.06, c equal to 0. So this is your E22 double dot, in which y is considered to be 0. This was for model 2. Here you see that we have considered y to be 0 in this model, E22 double tilde. So from the numerical simulation also, we get y double tilde equal to 0. And this is shown to be a locally asymptotically stable, this equilibrium point E22 double tilde, which is shown in figure 3. You can see the figure 3. So y is you're tending to 0. This red line is tending to 0. So time series graph for model 2 around the equilibrium point E22 double dot, double tilde, showing the stability behavior. We choose the following values for parameters for E23 double tilde. That is the interior equilibrium point of the model B. So these values we have taken, considered or assumed, and for these values, all the existence conditions of the equilibrium point and stability conditions for the equilibrium points are satisfied. And with the above values of parameters and taking the remaining parameters to be same as considered for E21 4 dot, it is found that under the above set of parameters, the equilibrium point E23 double dot bar, E23 double bar, that is interior equilibrium point, value is given by n double bar is this 9.2722, x double bar equal to 5.8182, y double bar equal to 3.4083, and c0 double bar equal to 0.0727, c double bar equal to 0.1584. This is locally asymptotically stable, shown in figure 4. So this is the figure 4, which shows the local stability of the model 2 for the interior equilibrium point. See. Now we do this comparison of model 1 and model 2. In this section, we do simulation and comparison for the equilibrium points E13 bar and E23 double bar of both the models, that is the role of effect of toxicant and the effect of harvesting on the underlying 3 species food chain system. See figures 5 to 10 and tables 1 and 2. So with the help of numerical simulation, we find out what is the role of harvesting, what is the role of toxicant on the existence or survival of the 3 species, that is prey, intermediate predator, and top predator. So here you see the time series graph for the model 1 in the absence of toxicant and constant yield harvesting, showing the stability. So when the toxicant is not there, so C0 and C both are not there. So we have only the graph for N, X, Y. And in this case, this is model 1. So we have constant yield harvesting. So it is shown to be this stability behavior. Yeah. Now time series graph for model 1 in the absence of toxicant and the presence of constant yield harvesting showing the stability behavior. So in the figure 5 we have not taken the harvesting as well as toxicant, but in figure 6 we are not taking toxicant but constant yield harvesting is considered, and we show the stability behavior of the NXY, that is prey, intermediate predator and top predator. Time series graph for the model 1 in the presence of toxicant and the absence of constant yield harvesting showing the stability behavior. So here we are not taking harvesting but we are considering the effect of toxicant in the intermediate predator. So this is shown to be stable. Time series graph, similarly we have the time series graph for model 2 in the same way as in absence of toxicant and constant harvesting. Then for model 2 in the absence of toxicant and presence of constant effort harvesting. Here we are then time series graph for the model 2 in the presence of toxicant and the absence of constant effort harvesting showing the stability behavior. So in all the we have 3 cases, that is no toxicant, no harvesting, no toxicant harvesting, and both toxicant and harvesting. We have considered simulated the variables which are showing the stability behavior. Now this figure 11 shows the variation of X with respect to time t corresponding to the effect of toxic and harvesting in model 1. So here you see that in the intermediate population we are taking the effect of toxicant as well as harvesting. So in model 1 we have considered constant harvesting and constant yield harvesting. So you can see that X, when harvesting and toxicant effect are there, so this bold line is there. Then if no harvesting and toxicant effect is there, then this is the bold dotted line. And when X is being harvested and no toxic effect is considered, then we have a small dotted line. This one, upper one, with light dotted lines. So from here you can see that when both harvesting and toxic effect are considered in the intermediate population, it has the minimum density. Because you see here, it has a minimum density. But when there is only when we have toxic effect and no harvesting, then slightly the population of intermediate population increases. So, but when we consider harvesting and no toxic effect, when there is no toxic effect and harvesting is there, then your predator population, intermediate predator population goes very high. You can see goes very high. So what we see that the harvesting is not that prominent as toxicant effect is there when we talk about the intermediate predator population. So toxicant, the effect of toxicant is more than the effect of harvesting in the intermediate population. You can see from this figure their density. So the effect of toxicant is more prominent than the effect of harvesting in the intermediate predator population. So this was an new result. So when we talk about the constant, when we take variation of X with respect to time corresponding to the effect of toxic and harvesting in model 2. So when we, instead of constant harvesting constant yield harvesting, we consider constant effort harvesting in the model 2, constant effort harvesting, then we can see here that when we, the population of the intermediate population is lowest when we take both harvesting and toxic effect. This is lowest. When there is no harvesting and toxic effect is there, then slightly the intermediate population increases, but it increases more than the constant yield harvesting. From the previous figure, you can see that it increases more than the constant yield harvesting. when we take the constant effort harvesting. Yeah. So, but in this case also, when harvesting, no toxic effect is there, but harvesting is there, the intermediate population, predator population, goes very up, and its density increases more. So in this case also, we see that the role of toxicant is prominent than the role of harvesting in the intermediate predator population. So here when we take the constant effort harvesting, then some regulatory body is there. So therefore, they regulate that the population should not go very low, and you should have a sustainable harvesting yield. So that's why when you take constant harvesting effort, then your population increases. When you don't. But in constant yield harvesting, I think if there is no regulatory system, so obviously their population will increase slightly. Now this is the figure number 13. Variation of nxy with respect to time t corresponding to the input rate of toxicant Q0 in model 1. So Q0 is the input rate of, so what will happen when we increase Q0? So 3 values of Q0 has been considered, and you can see that when Q0 is 0, so these are the 3 populations, N, X and Y. So this bold lines, when Q0 is this, Q0 is this, then this one, this and this. This is prey, this is intermediate predator, this is top predator. Okay. When Q0 is 0, what happens when we take Q0 equal to 0.35? Then the prey population increases, but the intermediate predator population decreases. So you see the interesting behavior over here, because when you increase the input of toxicant in the environment, and it is directly affecting the intermediate population decreases, and when the intermediate population decreases, obviously the prey population will increase. So from here it goes to here, you can see. And when the intermediate population decreases, then what will happen to your top predator? You see this one, it has also decreased, because top predator is not getting enough food for their survival, because the population of intermediate predator has decreased. So you see how the when we take the effect of toxicant in the intermediate predator population, then we see that prey population increases and the top predator population also decreases. So this is also an interesting dynamics which we have shown in this. And further you can see here Q0 is taken to be 0.75. So here you see prey population further increases and predator population further decreases from this red dotted line to blue dotted line. And top predator reduces further from red this one to light dotted line to light this blue. So this, when we are increasing the Q0, that is the input rate, and it is beneficial to prey population, but it is not beneficial to both the predator population. And it may happen also that if we take increase more the input of the toxicant, the predator populations may die out also. The similar results you see from for the model 2 also, when we take different values of Q0. Here also you can see Q0 0.1, then we take Q0 0.3 and Q0 0.1. When 0.1, then this is for N, this is for X, and this is for Y. Okay, that is prey, this is intermediate predator, and this is top predator. And the same when we increase Q0 equal to 0.3, this green one, you see here also prey population increases, intermediate predator population decreases, and your top predator population also decreases this here, you can see. And when we further increase Q0 0.4, the prey population further increases, intermediate population further decreases, and top predator also decreases. So you see how in food chain model, when we are talking the harvesting, and we are considering only the toxic effect in intermediate population, it is affecting both the prey also and its top predator also. So these were the very new results as got from the numerical simulations from the study of the food chain models under harvesting and toxicant. Now here what then we take the variation of nxy with respect to time corresponding to the constant yield harvesting model 1. Now we are taking the model 1 and we are changing the harvesting constant yield harvesting rates we are changing. So when H1 is 0.001, then what is happening? This is your prey population, this is your intermediate predator population, and then this top predator. This is your top predator population. When we increase the constant yield harvesting from 0.001 to 0.05, what happens? You see here, the prey population increases, the predator population intermediate decreases, and your top predator further decreases. So here also you can observe that when we are increasing the harvesting, constant yield harvesting, then similar phenomena is seen as we have seen for the effect of toxicant. That the prey population is getting benefit, intermediate population is decreasing, and since intermediate population decreasing, top predator is also decreasing. And when we further increase the constant yield harvesting rate from 0.05 to 0.1, we see that both the predator population die out. You can see here, and only the prey population will survive in this case. So you see that the effect of how the harvesting is also affecting the dynamics of the food chain model and the toxicant effect and harvesting effect. And this is the case when for the model 2, when we have constant effort harvesting. Here also we are taking different values from of the constant effort harvesting, constant effort harvesting, like from 0.01 to 0.02. We see, so 0.01, when we take the constant effort harvesting, that is E1, E2 equal to 0.001, then this is your prey population density, this is your intermediate predator population density, this is top predator population density, the green one, all the greens. Now when we increase the constant efforts harvesting from 0.001 to 0.05, you see that prey population increases, the intermediate decreases, and you see the top predator density tends to 0. Here you see it is going to 0. Almost it is 0. And when we further increase the constant effort harvesting from 0.05 to 0.2, the prey population further increases, the predator population dies out, and the top predator also dies out. So in the case of model 2, when we consider constant effort harvesting, similar results we get as in from the model 1 that we see here from figure 15, which we have seen. These also can be seen from the figure 16 in the case of model 2 also. So harvesting and toxicants are having deleterious effects on the food chain system, and these are the numerical values for different cases of model. So when the harvesting and toxicant is there, N is 9.2, this is 6.07, 3.57. When no harvesting and toxicant, this has already been explained with the help of figures, figure 7. So here when we have no harvesting and toxic effect, then your prey population is 9.2, and your no harvesting and only toxic effect, then X is 6.12 and Y is 3.6. But when there is harvesting and no toxic effect, then prey intermediate predator population and top predator have more values, and prey population has less values. So here you see that the toxic effect. Here also the harvesting is not that not that effective for the intermediate or top predator in this case. Similar numerical case, similar we find out the similar values when harvesting and toxic effect is there, no harvesting and toxic effect is there, harvesting and no toxic effect is there. Similar type of values we get in the case of model 2 also for NXY. So whatever we have explained from the, I have already explained in the figures. You can see here that effect of Q0, that is input rate of toxic in model 1. From figure 13, it is noted that when Q0 belongs to 0 to 0.75, then the equilibrium of prey population increases and equilibrium of both the intermediate and predator decreases as the values of Q0 increases. Effect of Q0, input rate of toxic in model 2. From figure 14, it is noted that when Q0 belongs to 0.1 to 0.4, then the equilibrium of prey population increases and equilibrium of both the intermediate and top predators decreases as the value of Q0 increases. Already have been explained in the figure. Effect of constant yield harvesting on model 1. From figure 15, it is noted that the equilibrium of prey population increases as we increase the value of H1 and H2, and equilibrium of intermediate and top predator populations decrease and tends to extinction when H1 and H2 both are increased simultaneously. Effect of constant harvesting on model 2. From figure 16, which we have already discussed, it is noted that the equilibrium of prey population increases as we increase the values of E1 and E2, and equilibrium of intermediate and top predator populations decrease and tends to extinction when E1 and E2 both are increased simultaneously. Now we come to some conclusion. So in this talk, we have proposed and analyzed a non-linear mathematical model to study the effect of toxicant on 3 species food chain system with predator harvesting. It is assumed in the model that the intermediate predator population is adversely affected by the toxicant concentration in both the models. The effect of constant yield harvesting on predator populations in model 1 and the constant variable yield harvesting on predator population in model 2. It is shown that the equilibrium point E1 to tilde of model 1 is unstable due to the effect of constant yield harvesting. From the stability of equilibrium point E2 to double tilde of model 2, it is concluded that the only prey and intermediate predator population will survive in the presence of environment toxicant, and the top predator populations would tend to extinction. See figure 3. The interior equilibrium points E1 3 bar and E2 3 double bar of both the models are locally and also non-linearly stable, showing the coexistence of all the 3 populations of prey and predator species. That is already explained in figure 2 and 4. However, from the equilibrium values, it is seen that the equilibrium density of top predator reduces and the equilibrium density of prey increases due to the presence of toxicant in intermediate predator, which I will also explain by figure. Finally, we have demonstrated the dynamical behavior of a 3-species food chain system with toxicant effect and harvesting with the help of numerical simulation to support analytical results. From numerical simulation, it is noted that the negative effect of toxicant is more on the intermediate predator population as compared to harvesting effect. See figure 11 and 12 and table 1 and 2. We have already explained this. Further, it may also be pointed out from figures 11 and 12 and table 1 and 2 that the harvesting and the presence of toxicant in the environment has synergistic adverse effect on intermediate predator population, and thus it's the prey population and the top predator population also affected simultaneously. One is getting increasing, prey is increasing, and the top predator is decreasing, just because of the effect of toxicant or harvesting in the intermediate predator population. So this was our few conclusions of the food chain model 1 and 2, or A or B, and these are the references. Thank you.
Thank you so much, Professor Mishra. It was excellent presentation. And let us see if there is some query.
Yeah.
Rata, do you see any question?
Checking, sir. Checking. Yeah, I think there is no posted question, sir.
Okay, I
Yes.
can see in chat all appreciation for Professor Mishra.
Mhm.
Sir, if you can hear me.
Yeah, I can hear you.
Yeah. So actually, I have a simple query. Like, did you apply these models in any real geographical area?
Actually, this is purely a conceptual model,
Right.
and it can be applied to even where we are having the like fisheries. We are having the harvesting.
Fisheries, yeah.
Like in that, we can have a food chain type of situation in like zooplankton, small fish and large fish.
Yes.
So, and there are other applications area where we can apply, but we should have for the real that for right for validation of the model, we should have some real data also.
Real data, yeah.
Okay. For that, you have to search or you have to do some experimental things.
Right.
It is not a one man's, not a mathematician can only do these things.
That's true. That's true.
You need some all the people from biology or ecology.
Exactly. Yes. Anyway, I thank you, sir, for sparing time for us from your busy schedule. And we look forward to future collaborations. And if any participant want to contact, I think they can reach out to you for help in their research field.
Sure. You can share my email address. And they can
yes, sir. Yes, we'll do that. In fact, they will have all YouTube this recording also.
Okay.
Yes.
So,
okay, with these words, once again, I thank our distinguished speaker. And
thank you for giving me the opportunity.
Sir, thank you. And for the participants, the next session today, it is a bit exception. It will not start at 2:30, but it will be at 5 p.m., 5 to 6:30 p.m. Because today's speaker, Professor Maya, is from University of Florida, USA. So because of the time difference, we have to shift the session. So please note that it will start from 5.